Swayam Prabha. Digital India. Educated India.
Hello student, welcome to the course on optimization methods for civil engineering. So, today I would like to introduce you what is optimization, and then I will also discuss about necessary and sufficient conditions for optimality. So, that I will discuss after that, but before that let me introduce what is optimization. Now, if I ask you, are you using optimization? The answer is, the word optimization may be very familiar or may be quite new to you, but whether you know about optimization or not, you are using optimization in many occasions of your day to day life. Let us see some example problems. So, what I would like to say here, that whether a person is familiar with optimization or not familiar with optimization. Suppose the layman, they are not familiar with the optimization, but still I can say that they are solving optimization problem in their day to day life. So, let us see some examples. I would like to give you a few examples. So, one of them is this person, he is a newspaper hawker. So, what he is doing basically, he is distributing newspaper in a colony. Now, question is that whether he is using optimization. So, I will discuss about that. Then second example is that lady is preparing some food, or you can say that she is preparing some recipe. As you can say that there is no link to optimization, but I can say during the process of preparation of food, or you can say during the process of your preparation of this particular recipe, she might be using some optimization technique, or I will explain that one, how she is actually solving an optimization model. Then third example problem is a forensic artist. So, what he is doing? He is trying to construct a face of the criminal based on the information he has received from the eyewitnesses. Okay. So, eyewitnesses has explained something, that this is the nose, this is the shape of eyes, this is the size of the eyes, or something like that. So, based on the information received from the eyewitness, he is trying to construct the face of the criminal. So, now I can explain, I will explain how he is also solving an optimization model. Okay. Apart from that, suppose if you look at the ant, okay, so when they are moving or whatever social behavior they have, they are also using optimization. Maybe we can have some other example problems. So, when we will discuss about the meta heuristic optimization method, but today I will take these 4 example problems, and I would like to explain that how these people, the newspaper hawkers, during cooking, the forensic artist and ant colony, how they are using optimization, or by knowingly or by without knowing they are using optimization, as I said. So, let me explain that one. So, let me take the example of newspaper hawker. Okay. So, what he is trying to do? He is trying to distribute the newspaper in a colony. Okay. So, maybe there are different quarters, then suppose he is trying to distribute in an education institute. So, he has to distribute this newspaper maybe in the residential complex, then to the hostel, to the admin block, okay, to the girls hostel, boys hostel, something like that. Now, the first day he does not have many information about that colony. So, what he will do? He may have some planning based on the information he has received. So, he will try to distribute the newspaper. Then once he is distributing the newspaper on that day, so he will have some experience that okay, if I go to this quarter first, then I will go to hostel, then I will go to admin building, and probably I can distribute this newspaper in a minimum time. So, his objective is to distribute the paper within a shorter duration of time. So, what he is doing basically, he is trying to minimize the time of distribution here. So, you can say that he is trying to solve an optimization problem. So, what is the objective function here? The objective function is to minimize the distribution time. So, you will surprise that after few days, okay, after few days, maybe first day he has distributed this, he has chosen some route, then second day he will modify that one, then he will try to minimize the time, and you will see that after few days, maybe after 7 days or after 6 days or maybe before that, so he has actually obtained an optimal route, or that is the optimal solution of this particular problem. So, what he is doing? He is trying to minimize the time. So, you can say that he did not solve any optimization problem mathematically, but with some experience or he is basically trying to find out a solution so that he can distribute this newspaper within a shorter duration or he is trying to minimize the time. Then second example is, suppose the lady is preparing some food, or you can say the recipe. So, how we are preparing a recipe? So, it is a combination of some spice you are putting on it, and the duration of heat basically, or you are heating that recipe. So, that is one your parameter. So, what will happen? Suppose the first day when you do not have any information, so you are putting some spice based on your experience, and then what you will do, that you will test it, and after that you will try to modify the recipe, maybe combination of different spice you will basically you will send, and after few days what will happen, or you can say with experience, then you will actually find out an optimal combination and optimal time, basically at what time you want to put this particular spice. So, you can find out an optimal combination of that one. So, that way what you will have with some experience. So, you are mathematically you are not solving an optimization model, but actually you are solving an optimization model, and you can say this is an iterative based optimization model, and after few days you will have basically a recipe. So, what is the objective function here? The objective function is that I would like to maximize the taste, okay, the taste here, and what are the decision variables here? That how much spice you are putting, at what time you are putting, what are the spice you are putting. So, these are the decision variable. Okay. So, that way she is also solving an optimization model. Then third example is a forensic artist. So, what he is doing basically? So, he has the information from the eyewitness. So, eyewitness will say that basically, so this is the eyewitness will give you the description about the criminal, and based on that he will initially first he will construct a face, and then he will take the feedback from the eyewitness. Okay. So, whether his nose is similar to that criminal, then eyewitness will give you no, this is something like that. So, then he will modify that one, and then he will make it second sketch, third one, fourth one, fifth one, like that. Then after some time you will see that after some iteration you will see that he has constructed the face of the criminal. So, what is the objective function here? The objective function is to maximize the similarities between his drawing and the criminal face basically. So, and with some iteration, so he will be able to do that, and this is basically he is also solving an optimization model. Then the fourth one is an ant colony. So, I will give an example of that one. So, let us see this ant. So, what they are doing? So, there is a nest and they are trying to search the food. You can also do this experiment, and you will see that these ants are moving in a straight line. Basically, what they are trying to do, this is the shortest distance basically. So, you can see, suppose the ant nest is somewhere here and they are moving towards the food, and you can see that they are moving in a straight line if there is no obstruction. Now, let us see, you can do this experiment. So, I am putting some obstruction here. Now, obstruction are that if you put the obstruction in such a way that suppose initially what ant will do, that they will try to move because of this obstruction, the ant cannot move like that. So, they will move, some ant will move in this direction, some will move in this direction. And you will see after some time that because this is the shortest distance, okay, this is the shortest distance, and you can see that no one is there on this side, and everybody is moving in this route, because that is the shortest distance. Okay. So, here also they are trying to solve an optimization model, or they have actually solved an optimization problem, but without knowing any mathematics. Okay. So, they have a different mechanism, and you can say that whatever method they have used, based on that there is an meta heuristic optimization algorithm known as ant colony optimization. So, ACO, that is ant colony optimization. So, this is basically based on the behavior of this ant, basically how they are trying to source food through a shortest distance, and based on that actually this algorithm has been developed, and this is a meta heuristic optimization algorithm. So, what I would like to say, that whether we know optimization or we do not know optimization, so we are actually using optimization in our day to day life. So, you can say suppose when you are preparing for your exam, it is not that you are preparing arbitrarily. Okay. So, with some experience, so what you will do, you will have some planning, and when you will have done optimal planning, because what you have to do, that within that particular duration, okay, so you have to prepare for the exam. So, you should have some planning, and there also actually you are trying to solve an optimization model without basically knowing the optimization. So, what I am telling that we are using optimization in our day to day life without knowing about the optimization, Now, let us take an example problem. So, this is a simple example problem. So, a farmer has 2400 meter of fencing, okay, and want to fence a rectangular field that borders a straight river. He needs no fence along the river. What are the dimension of the field that has the largest area? So, what is the problem here? So, problem here is the farmer has 2400 meter, that means 2400 meter of fencing. So, that is the material he has, and he want to fence a rectangular area that borders a straight river. Okay. So, basically on the bank of the river, and he needs no fencing along the river. So, on the river side there is no fencing, on the other three side you have to put the fencing. Now, question is that what is the dimension of the field that has the largest area. Okay. Now, suppose this is the river, and what I can do basically, so on the river side you do not need fencing, this side you do not need fencing. So, you need fencing on the left side, on the right side, and on the other opposite side of the river. So, this is also a solution, that I can put 100 meter on this side and 100 meter on this side, and this side this is 2200. This is also a solution, and I can find out what is the area. Now, second solution is maybe 700 meter here, 700 meter here, and 1000 here. So, this is also a solution, and the third one is I can also put 400 on this side, 400 on this side, and 1600 on this side. So, these are possible solution of this particular problem. Now, what you have to do basically? So, we need to find out the dimension of this rectangle, so that this 2400 meter of fencing means suppose I can use, and the area will be the largest area. So, this is an optimization model. So, here what is your objective? the objective is to maximize the area of maximize the area of this of the rectangle. Okay. So, what I can do that I can take this variable. So, this is your x. So, this is your this dimension is x and this is your y. Okay. This is your y. So, therefore, I would like to maximize the area. So, what is your area? X into y. Okay. So, this is my objective function, but there is a constraint. What is the constraint here? The constraint is that x plus twice y. Okay. So, this x plus twice y, that means the perimeter. So, reverse side there is no fencing, there is no fencing on this side, on the other three side we have fencing. So, that is x plus twice y should be equal to 2400. So, this is an optimization model. So, here we have the objective function, that is maximize the area. So, maximize f equal to x y, x into y, and subject to there is a constraint, and constraint is that the total material availability is 2400. So, therefore, x plus twice y equal to 2400. So, the problem actually, so whenever you are getting a problem, so you may not get you may not get a problem in this means suppose in mathematical form. So, somebody will explain that one, that in this case suppose the farmer has 2400 meter of fencing. So, this is the fencing he has, and he wanted to fence an area. So, the problem will be described like this, and then we have to formulate the optimization model, and once I solve this problem. So, I will get the dimension, what is the value of x and what is the value of y, I can find out. So, I will discuss about the solution part later on, but right now I would like to discuss that how to formulate an optimization model. Okay. Let us take another example problem. A manufacturer need to make a cylindrical can that will hold 1.5 liters of liquid. Okay. So, this is a design problem. I would like to design a cylindrical can here, and the capacity of the can is 1.5 liter. Okay. Determine the dimension of the can that will minimize the amount of material used in its construction. Okay. So, what you have to do here? So, here we have to design a can. So, the capacity of the can is 1.5 liter. Okay. So, that is the capacity of the can, and what you have to design? Design means I have to find out the dimension of this particular can where the capacity of the can is 1.5 liter and the cost is minimum. Okay. So, I have to find out the dimension of the can. So, where cost is minimum, that means I would like to minimize the cost here. At the same time, the volume of this can should be equal to 1.5 liter. Let us see how we can formulate an optimization problem. Okay. Now, this is the can, it is a cylindrical can. So, therefore, the dimension of this is the height of this can h, and the radius is r. Okay. So, this is a cylindrical can. So, this is the height and this is the radius. Okay. So, now if I say the material cost, so that means this is the surface area of this can. So, area is twice by r into h. So, twice by r into h, and then we have to take the material used at the top and at the bottom. So, that is pi r square, and at top and bottom. So, this is twice pi r square. So, therefore, what is the total material use? This is twice pi r square plus twice pi r h, and what is your objective? I would like to minimize the material cost. Okay. So, I would like to minimize this one. So, this is minimize A equal to twice pi r square plus twice pi r h, and there is a constraint here. What is the constraint? The volume. So, what is volume? That pi r square into h, that should be equal to 1500. So, it should be equal to 1.5 liter, and all dimensions are in centimeter. So, here this r is in centimeter, h is in centimeter, and therefore, the volume we have converted, if we convert 1.5 liter into centimeter cube, then it will be 1500 centimeter cube. Okay. So, now this is your optimization model, and here what we are doing, we are trying to design a cylindrical can with cylindrical can of capacity 1.5 liter. And now, if I solve this problem, so I will get the value of R and H, and that will be the optimal solution. And if you are using that, so the cost of this or construction cost of this particular can will be minimum. Okay. So, we will find out what is the value of R and H anyway. So, today we are not solving this problem. So, we are just trying to show you how you can formulate an optimization problem. The third example problem is a truss design problem. Okay. Now, in case of truss, what are the objective? So, objective is, one is the topology optimization. I can say that optimal connectivity of the structure. Okay. So, one objective may be, I would like to find out the minimum connectivity, or I can say optimal connectivity of this structure. We call it topology optimization. And second one is, once you are getting the minimum connectivity or optimal connectivity, then I would like to minimize the cost of material. Okay. So, minimum cost of material, and we can say that optimal cross section of all members. Okay. So, this is another objective. So, I can have topology optimization, that means I would like to find out optimal connectivity of the structure. So, what does it mean? Whether suppose there may be other connections here. Okay. So, if I go for the first objective, so what are the connection actually I need basically, and that is I can say that optimal connectivity. So, in this case, suppose this is not required, this is not required, this is not required. So, finally, what I am getting? So, I am getting this particular your structure. Okay. Now, in the second objective, what you have to do? We have to find out the optimal cross section of all the members, so that the material cost is minimum. So, here objective is the minimization of the material cost. So, we will consider the second objective here. The design variables are the cross sectional area of the members, that means there are 7 members here. So, there are 7 members here, that means A1 to A7. So, this is A1, A1, A2, A3, A4, A5, A6 and A7. So, we have 7 member. So, we should have 7 design variable. Okay. But using symmetry, so if I say that A1 equal to A7, okay, so or A7 equal to A1, and similarly A6 equal to A2, that means A6 equal to A2, and A5 equal to A3. So, therefore, if I use the symmetry of the structure in this case, that particular problem. So, if I say that A7, the cross sectional area of the 7th member equal to cross sectional area of the first member, then A6 equal to A2 and A5 equal to A3. So, in that case, what I can only consider A1 to A4, because A5 equal to A3, then A6 equal to A2 and A7 equal to A1. So, I have actually reduced the design variable. So, this is also an important step in case of optimization model. So, because when your number of variables are more, so in that case solution will be little bit, or solution will be complicated. So, therefore, you should always look at whether it is possible to reduce the number of design variables. So, in this case by using symmetry, so we can actually reduce the number of design variable, and as I said, the earlier design variable was 7 and now we have only 4 design variable. Now, let us see what is the objective function. So, objective function, as I said, that the minimization of the material cost. Okay. So, what is your material cost? So, material cost of all these structure. So, we have actually, so A1 is this member and this member. So, total length of this A1 member is 1.132 L into cross sectional area will give you the volume and basically. So, this is the volume of the or you can say this is the material you need for A1 and A7 member. Similarly, for A2 that is twice L into A2, and similarly for A3 I need 1.789 A3 into L, and for A4. So, we have 1.2 A4 into L. So, this is the total material used in this particular truss, and I would like to minimize. So, here what I would like to find out? I would like to find out what is the value of A1, A2, A3 and A4, so that the material cost is minimum. Okay. Now, this is your objective function. Then what are the constraints? So, one essential constraint is the non-negativity of design variables. So, what does it mean? That this design variable, what are the design variable here? The A1, A2, A3 and A4, they are the design variables, and these variables cannot be negative. So, this cross section cannot be negative. So, therefore, the non-negativity of the design variable is one of the essential your constraints. So, always you should put that one, and therefore, A1, A2, A3, A4 should be greater than equal to 0. It cannot be negative. Now, is it complete now? It is not complete, because if I solve this problem, so what I will get? I will get the value of A1, A2, A3, A4 all will be 0, and that will give you minimum material. Okay. But that will basically that structure will not exist if I say A1, A2, A3, A4 all are 0. So, therefore, this problem is not complete. So, what you have to put? You have to put the constraints. Okay. So, what are the constraints here? The constraints are that the member, the cross section of the members should be sufficient enough to take the compressive compressive force as well as tensile force. So, I can do the analyze here. So, what are the forces here? In AB, the forces here is minus p by 2 cosec theta, and the force is the compressive in nature. So, negative means compression and positive mean tension. So, similarly, in member AC, so we have positive means it is in tension, that is p by 2 cot theta. In BC member, so BC, so this member, so it is p by 2 cosec alpha. So, here, so this is theta and this is your alpha, and member BD, this is this member, and that is again the force is compressive force, and that is p by 2 within bracket cot theta plus cot alpha. So, these are the force. So, now whatever member you are you want to design, so the cross section should be sufficient enough to take this stress or to take this your compressive and tensile force. So, therefore, the first set of constraints are, so this is the stress developed here, that is p cosec theta by twice A1, and this should be less than the permissible compressive stress of the material. Okay. So, similarly, that the second member, that is AC member, the stress is p cot theta by twice A2, and that should be less than the permissible tensile stress of this particular material. Okay. Similarly, for the member BC, that is p cosec alpha by twice A less than SYT, that is in tension, and for the member BD, that is p by twice A4 within bracket cot theta plus cot alpha should be less than the permissible compressive stress of the material. So, therefore, these are first set of constraint. That means, if you are putting this constraint to your optimization model, then whatever cross section you will get. So, this will ensure that the members are or cross sections are sufficient enough to take the tensile force as well as compressive force developed within the member. Okay. So, what are the other constraints? The other constraints may be the compression members. So, what are the compression member here? AB and BD. Okay. So, this is AB and BD, okay, this member AB and BD. So, these two are your compression member, and this member should not fail in buckling. Okay. So, it should not fail in buckling. Okay. So, therefore, you have to put this constraint in order to prevent the buckling, that is P by twice sin theta less than equal to pi e a1 square divided by 1.281 L square. And similarly, for a member BD, that you have to put P by 2 within bracket cot theta plus cot alpha should be less than equal to pi e a4 square divided by 5.76 L square. So, if you are putting these two constraint along with the first set of constraint, so then whatever cross section you are getting, those cross section will be safe enough for that to take the compressive as well as tensile stress, and your member will also not fail, and your member will also not fail in buckling. There may be another constraint, that the deflection, suppose the structure is safe, but there may be some deflection here. Okay. So, I can say that this deflection is delta. Now, what I can do basically, so I can put another constraint, so which will give you the deflection, and deflection if we calculate at point C here. So, deflection is PL by E within bracket 0.566 divided by A1 plus 0.5 by A2 plus 2.236 divided by A3 plus 2.700 divided by A4, and this is the deflection. This will give you the deflection at point C. Okay. So, you can say delta, and this delta should be less than equal to delta max. Okay. So, I can put this constraint also. So, once you are putting that one, that you are your truss will also be safe from deflection point of view, and whatever you mean, suppose whatever value of cross section you are getting. So, in that will give you the deflection, that will give you a structure where the deflection will be less than your delta max. So, I can define this your delta max. Finally, if I put all these constraints, then my optimization model will be something like that, that I would like to minimize the material cost. Okay. So, this is the material cost, and these are the constraints, and first 4 constraints are coming from the compressive forces and tensile forces. These 2 are coming from buckling, that means these 2 constraints will ensure that the structure is safe from buckling, and the third the last one will ensure that the deflection is less than delta max, and then I can put what is the lower bound of the variable, design variable, that is A1, A2, A3, A4 should be within this particular range. So, I can define, and overall this will be my optimization model, and if I solve this problem, so I will get the dimension of the truss, that means cross section of the members, and your truss will be safe from compression, from tension, then from buckling, and as well as the deflection will be less than delta max. Okay. So, this is your another example problem. Now, let us take another example problem. So, we call it traveling salesman problem. So, here the problem is there are few cities. Okay. So, there are suppose city A, city B, C, E and D. So, now a person would like to visit all these cities, and he basically want to visit it within minimum time. Basically, what is the objective here? Just like the newspaper hawker, he is trying to distribute the newspaper. So, here the salesman is willing to visit all these cities within a short time, okay, short duration. So, here the objective is minimization of time. So, one solution may be, this is one possible solution, that you are from A to B. So, you are starting from A to B, then E, then D, then C basically. So, A to B, okay, then B to E, okay, E to D, then D to C, and C to finally A. So, this is one solution, and the second solution may be something like that. So, you are coming from A to B, B to C, then C to D, D to E, and finally E to A. So, here what you want to find out? So, you want to find out the optimal route here. Okay. So, whether you are from A, you are coming to B or coming to C, and from C whether you are coming to B or coming to D, something like that. So, you need to find out a network, or you need to find out a route, and which will give you, or which will give you an optimal route basically, and in this case you are minimizing the time. There may be some other constraint here, because we can put different constraints like availability of the flight and other your transportation modes, so that we can put it, and based on that those constraints. So, you need to find out an optimal route so that you can visit all these cities for your work, and basically you are trying to find here an optimal route. Okay. So, this may be an example problem. Suppose a particular flight is trying to cover all this city, okay. Suppose a flight. So, in that case, how a flight will basically start. So, maybe from Mumbai, whether he will go to Bhopal first or he will go to Delhi first, and like that. So, this is one route basically. The flight is moving from Mumbai to Bhopal, Bhopal to Delhi, Delhi to Guwahati, Guwahati to Calcutta, Calcutta to Chennai, Chennai to Bangalore, and finally you are reaching again Mumbai. So, this may be a flight route. Okay, nowadays you have seen that flights are actually giving connectivity to different your location. As you see that if you if somebody is trying to go from Mumbai to Delhi, so maybe he can take this flight, and but when he is the flight is going from Mumbai to Guwahati. So, maybe from Mumbai to initially to Bhopal, or Mumbai to Delhi, Delhi to Guwahati, or something like that, or you may have some optimal route. Okay. This is another example problem, we call it traveling salesman problem. So, we will try to solve some problem related to this aspect also, apart from our other civil engineering problems. Now, what is optimization? So, with the example problem we have discussed. So, let me define what is optimization. So, optimization is an act of obtaining the best result under a given circumstances. So, what is optimization? So, optimization is the act of obtaining the best result under a given circumstances. So, we have seen some example problem. So, under those circumstances, we would like to find out what is the best result, and that is basically known as optimization. Okay. So, optimization is the mathematical discipline which is concerned with finding the maxima and minima of functions possibly subject to constraint. Okay. So, it is a mathematical discipline, which is concerned with finding the maxima and minima of a function possibly subject to a constraint. I think in your school level you have already solved this finding minima and finding maxima of a function. So, I think already you have done using calculus. So, I will also explain that one. Suppose this is a function, this function and this is the minima of this particular function. So, if I say this is a function, and minima of this function is somewhere here, and we generally denote it by your x star. Okay. So, this is x star. Okay. So, now this function is f equal to x minus 5 whole square. So, this is the equation of this particular function, and what we know basically. So, how to find out this minima or maxima? So, I will take the first derivative. Okay. So, I will take the first derivative. So, what is first derivative here? The twice x minus 5 and first derivative will be equal to 0, and if I solve it, so I will get minima of this particular function, and that is x equal to 5. So, this is the solution, and this is the minimum point of this particular function, and I would like to find out, and that is basically known as finding minima or maxima of a function. Now, let us take another function. So, this is another function, and here the maxima of this function is somewhere here. Okay. So, this is the maxima of this particular function, and maxima is at 0. So, in this case the minima was at 5, and in this case maxima is at 0, and suppose this is the function is 25 minus x square. So, this is the function, and I would like to find out the maximum point of this particular function. So, what I will do, I will take the first derivative. The first derivative is twice x equal to 0, and if I solve it, I will get the solution, and that is x star. So, as I said, so we put star to denote the optimal point. X star means that is an optimal point. Okay. So, either minima or maxima, or maybe an inflection point. I will also discuss what is inflection point. So, in this case the solution is x star equal to 0. So, I am getting this one, and I think you have already solved this type of problem in your school level. So, this is called the finding minima or maxima of a function. So, if I take a two variable problem. So, in this case suppose this is the function is minus x square plus y square plus 4. So, this is the function, and I would like to find out what is the maxima of this function. So, maxima of this function is somewhere here. So, what I will do, I will take derivative with respect to x, and I will take derivative with respect to y, partial derivative with respect to x and partial derivative with respect to y, and if I equate it to 0 and if I solve it, so I will get the optimal value, or I can say the maximum point of this particular function. So, we are taking derivative. So, derivative is del f by del x equal to 0. So, if I do that, so I will be getting minus twice x equal to 0 and x star equal to 0, and similarly if I take derivative with respect to y, then twice y equal to 0 and then y star equal to 0. So, therefore, the solution of this function is 0 0, okay, or you can say optimal solution, or you can say the maxima of this function is at 0 0. Okay. So, I think already you have solved this type of problem in your school level. So, what we are doing here, we are taking derivative and then we are equating to 0, the derivative value is 0 at your optimal point. Okay. Thank you very much.